Yes, sir.
Okay, so R1 and R2 are going to be parallel. So I'm going to consider that Thevenin resistance as RB. So RB will be equal to R1 parallel to R2. So you know for Thevenin's theorem, you have to find R Thevenin and V Thevenin. R Thevenin we have find, R Thevenin we have found. I'm going to rename it as RB. So RTH will be equal to RB equal to R1 parallel to R2. V Thevenin is the voltage across R2. If you apply potential division, voltage division technique, total voltage is VCC. I am measuring it across R2. So VT equal to total voltage into that resistance divided by that resistance plus opposite resistance. So VT will be equal to VCC into R2 divided by R1 plus R2. So once I know RT, RTH and VTH, I can simplify this circuit as shown here like this. So R Thevenin between will be available at the base and VT will be replaced here. So now analyzing this circuit becomes very, very easy for me. Rather than having a circuit with 4 resistances, now the circuit is having only 3 resistance and it is having only a simple loop, only a single loop at the input side. Are you all able to understand how this circuit is simplified to this circuit? It is very, very important to know how Thevenin's theorem makes your circuit very simple. Is it clear for everyone how to find RTH and how to find RB? Or should anybody want me to repeat this concept of finding RTH and VTH again? If things are clear, I'll move to the next calculation. Otherwise, I'll explain RTH and VTH calculation again, but you have to say that. Is it clear, right?
Sir, yes, sir. Can you repeat it once?
See, I am applying. See, why I am simplifying this circuit is I want to make my circuit analysis simple. So, you have studied so many network theorems which make your job simple, right? So, I'm going to apply Thevenin's theorem at the base. So, when you apply Thevenin's theorem at the base, first thing you have to find RTH. For finding RTH, what you should do, you have to remove all the voltage sources. If you have voltage source, you have to replace it by shorts, replace it by ground. You have to short it. If you have a current source, you have to open it. Okay, so if you see that I when you analyze the resistance R1 and R2, one end of R1 is connected to this point, another end of R1 is grounded. One end of R2 is connected to this point, another end of R2 is grounded. So RTH will be R1 parallel to R2. That is your Thevenin resistance. For better clarity, I am replacing the Thevenin resistance by RB because this is available at the base side. So I am replacing RTH by RB. Okay. And now you have to find the Thevenin's resistance VTH. So finding Thevenin's resistance VTH, you are going to apply the potential division technique. So VTH equal to total voltage into that resistance divided by that resistance plus opposite resistance. So VTH equal to VCC into R2 by R1 plus R2. This is VTH. So now this circuit becomes simplified here. So wherever I'm going to use VTH and RB, I'll be using the simplified expression and not the actual expression. Is this now clear how the circuit is getting simplified? Or still you are having doubts on this? You have to be very thorough in applying theorems across your circuit. That's why I said this subject is combination of basic electrical engineering and electron devices. Unless you know the concepts of both, it will be very difficult to immediately understand how theorems are applied in the circuit. Is it clear?
Yes,
Any
sir. Clear.
doubt? Okay. Yeah. Okay. Okay. Now we are going to simplify here. So the how we are going to see how the emitter resistance is going to uh, see here the emitter resistance RE. Whenever you have a resistance, you will have an voltage drop. So this emitter resistance will have an voltage drop, which is the direction to reverse bias the emitter junction. Okay, for the transistor to, this voltage across the emitter resistance Re, since you have a resistance here, this will tend to reverse bias your emitter junction. This will tend to reverse bias your emitter junction. Okay, but always we need the emitter base junction to be forward biased, right? So for that you need a constant biasing in the base emitter junction. So for that constant biasing only we are adding this resistance R1 and R2. Okay, so for the transistor to remain in the active region, the base emitter junction has to be forward biased. Okay, so for the transistor to remain in the active region, the base emitter junction has to be forward biased. So the required biasing is applied to the potential divider R1 and R2. Okay, so the required biasing is applied because of this potential divider VCC R1 and R2. Okay, so the adding this emitter resistance is going to reverse bias your base emitter junction, but I am overcoming that reverse bias in the base emitter junction by the potential divider VCC R1 and R2. Okay, so this VC, this voltage across R2 will ensure that this base emitter junction is always forward biased. The base emitter junction is always forward biased. So that's how you ensure the transistor is always on and the Q point is exactly fixed in the center of your DC.